happens anytime you go over integrated by parts?
Yes. Let me get through the new material first, and then we can go back because I would just want to make sure I cover the material first, but I'll definitely put after that. If not, constipating that's in the next one. Yeah, that was on the extra practice sheet section on the website. That's where the problems were.
I didn't get to look at it. That's kind of why I asked.
All right.
No, I had an exam Saturday,
so maybe it's best to leave that until Wednesday, so you have an opportunity to take a look at that practice sheet, and then we'll go over it. But definitely I'll budget some time, right? Because it is a very important topic, and also it's going to work its way into some of the stuff we do here. Anyway, objective to learn how to apply trig substitution and finding integrals. So these are cases where you're given an algebraic expression and you want to use your knowledge of trig functions to help you integrate. And basically it's taking situations that might otherwise be not integrable, if that's the right way of saying that, and it actually makes it something you can actually integrate. So I'm going to talk about the different cases and then we'll get into some examples. So the first case, it involves sine, but let me just talk about the structure of the triangle first. Okay. In each of the cases involving a trig substitution, view, zoom, let me go to 200%. In each case, you're going to want to draw the picture. It's going to be pretty helpful. All right. So we'll have a theta, a right angle, and then from there, it really just kind of depends on what trig function you're using. So in this case, we're using the sine function, and we're defining sine as the ratio of a variable to a constant, u over a. Right? So the trig ratio associated with sine is opposite over hypotenuse. All right, so the opposite side would be u, the hypotenuse would be a, and then using Pythagorean Theorem, we would solve and get the square root of a squared minus u squared. All right. And so what we want to do is when we're given an integral, we want to take note of what type of radical it involves. Specifically, cases that involve funky radicals that might be trig substitutions. And so once you identify what kind of radical it is, then you can apply the appropriate substitution. Right? So we get an alternative ratio here of the square root of a squared minus u squared over a. I don't think that's memorization as much as it is understanding a concept, because what I want to do when I'm doing a trig substitution is I want to swap out the funky part of the integral. All right. So in that case, or in most cases, it's going to be the radical. So I'm going to swap that out, and anytime I can incorporate a constant, that's going to make my life easier. So what's usually going to happen is that these parts are going to be built into the problem, but I want to swap it out for these things because they're going to be easier to work with. Right? Anytime you can incorporate a constant, that's going to be a good thing. So our alternative ratio is determined by where the radical is and where the constant is. Right? In this case, it'll lead to a cosine because the radical is my adjacent side in the triangle, and the constant is the hypotenuse. If I take the adjacent side and divide it by the hypotenuse, I'm going to get the cosine ratio. All right. And so it's out of context now, but you'll see just exactly how everything fits together in a little bit. Right? But it is all going to come down to your ability to construct the triangle. And that ties together with what we were talking about last week when we were discovering all of those derivative rules for inverse trig functions. So basically, I'm kind of getting at the idea that inverse trig is going to work its way into this. All right? Maybe you want to use the tangent ratio. Maybe a tangent ratio is more appropriate. And that's for integrals involving a squared plus u squared. All right, so if this is my theta, this would be my opposite side, and this would be my adjacent side. Tangent is opposite over adjacent by definition. So opposite, adjacent, hypotenuse, square root of a squared plus u squared. Or u squared plus a squared, it doesn't matter. All right? But it's the same thing. If again we're taking the ratio of the radical part to the constant, the radical part again is the hypotenuse. The constant part is the adjacent side. So I want the ratio of the hypotenuse to the adjacent. Hypotenuse, adjacent. I zigged when I should have zagged. The ratio of hypotenuse to adjacent by definition is secant. So that tells us to use a secant ratio as my alternative function. Again, out of context, what does all this mean? You won't know until we get into particular examples, right? The last possibility is if you have an integral involving u squared minus a squared. So hypotenuse, adjacent. Hypotenuse is u. The adjacent is a. I have an angle theta. The missing side would be the square root of u squared minus a squared, just based on simple Pythagorean theorem. All right. So again, if I'm taking the ratio of the radical, all right, that's the opposite side. So that's my opposite side. So the constant, which is my adjacent side. Again, my adjacent side. I'm looking at a ratio of opposite over adjacent, which leads us to the tangent ratio. All right. So that gives us a sense of the structure of the different expressions that we're going to use. But, like I said, for the last two cases, it's not going to make much sense until we see it in action. All right. But if you always have the idea in mind that you're going to have a u and an a, it's going to create a triangle, and then you're looking to take the ratio of the radical to the constant, then that's the framework of everything that we're going to need. And that's a good place to get started. And that's where all this stuff comes into play. All right. So one function is always u over a, variable to constant. The other function is always a radical to the constant. I don't know why it comes up with like this double radical symbol. Just want to clarify. That's just the transition from Microsoft Word to PDF. There is no new funky symbol that I'm introducing today called the double radical. That's not a thing. The square root of a square root is just a fourth root. So we don't. It's just the way it happens. I don't know why it does that. So don't get confused by the notation. That's just a regular radical, just a square root radical. All right. It breaks my heart every time I see it. All right. A particular example. And this stuff gets really funky when you start mixing concepts together, where I would say just find the antiderivative. Not find the antiderivative using a trig substitution. Find the antiderivative by using integration by parts. You know, it's just find the antiderivative where you have to figure out what it is. So then you look at this and say, all right, well, is this, I don't know, is it u substitution? Is it integration by parts and partial fractions, which we haven't learned yet? Is there a trig substitution? Fun fact, in a lot of these cases, there's the two ways to go about doing it. One way is to use a trig substitution. Another way is using techniques that we've already covered. There is a way to do this that involves breaking up this fraction into two separate fractions, using u substitution and knowledge of inverse trig functions. It'll get you there. It's not as elegant as the method I'm about to show you. after I'm done with this particular method, you may not look at this and think the word elegant, but it is considered to be that. All right, I'm going to draw a triangle. I want it to go the other way, so don't draw it yet. I don't know why it doesn't allow me to do it any way I want. So I just have to flip left, right. Okay. It really doesn't matter which way you draw your triangle. I like it this way only because it's consistent with what a reference triangle in a unit circle would look like. And if anything, I mean, I'm consistent to a fault. Consistently late, you know. Today I was on time. Early even. That's one of those when you're late for work often enough, and the boss is like, you've been late like 5 minutes every day for the last week. And then you're like, yeah, but what about that time I came in an hour early? Doesn't that like balance it out? No, it does. So, anyway, so I need to define this triangle somehow. So how do I get my U's and A's? Well, one thing that was pretty consistent on the previous page, and we could flip back to it for a second anyway, is that looking at our radicals, there was a sum or product of a squared and u squared. Sometimes it was the u that came first, and sometimes it was the a that came first. But there's always a sum or product of a's and u's. So basically it's telling me that the a is going to be the constant component, and the u will be the variable component. Right? So from here, what I can do is just grab this guy. That's going to be my a squared. And I'll take this one, and that's my u squared. All right? So off on the side, I'm going to write u squared equals x squared. And a squared equals 16. I'm going to show way more detail here than you probably would show yourself when you were doing this on a test or quiz or anything, but it's for a reason. So I need to know the a and the u, so let me make a note of that. U would be equal to x, a would be equal to 16. A would be equal to 4, because that's how math works. All right. So now it begs the question, what do we do? All right, so the u and a values are going to get placed on the triangle in some capacity. It's just a question of where. So what I want to do, and again, I'm just kind of pretending that I'm inventing this process, and also, you know, on the off chance during a test, what happens? And you get a rule. What can you do? You don't want to be pulled into rules because things go south. You got a problem. All right. I need to manufacture this radical. All right. So let's try some possibilities. Let's say I put my u value purple. I'm going to put my u value, let's say here, and my a value, I'll put it here. Using the Pythagorean Theorem, all you have to do is ask yourself, would I get, for the hypotenuse, the missing side, would I get the square root of 16 minus x squared? No. What I would get is the square root of x squared plus 16, right? And just Pythagorean Theorem is going to get me a radical, but not the radical I want. So clearly that's not the correct placement. So we move some things around. And again, this is assuming that you're either unable or unwilling to memorize the rules on the previous page. I would be unwilling. So maybe I put the 4 here, and I'll put the x here. All right, would that do the trick? Missing side would be the square root of 16 minus x squared. Hey, that's what I need. All right, but on the previous page, I said that, what's that? Exactly. So that's the idea, because on the previous page I just got through saying that you would use a sine ratio, but here I'm justifying that you would actually use a cosine ratio. In the end, it's not going to matter, because let me do a clone. If I were to put the 4 here with the x here, I would get the same ratio. So in the grand scheme of things, it really doesn't matter what the rules say on the previous page, as long as you can come up with the placement of your u and a values such that the missing side is the same as the radical contained within your not trig function, your integral. All right. So at this point, we can choose. I'll use the second one only because it's consistent with the rule that I have on the previous page, but it's going to work either way. All right, so now we have a well-labeled triangle, and that's, like diagrams are really useful, but only if they serve a purpose, really. So I need the ratio of the variable to the constant. All right, so ratio of variable to oh, that's too thick. What did I just do? Undo. I can't even explain remotely what just happened. All right, variable to constant. That's one relationship that I need. And I also need a ratio of radical to constant. All right, the variable to the constant would be x over 4. Because the variable is the opposite and the constant is the hypotenuse, opposite over hypotenuse would be the sine ratio. All right. Now the radical is the square root of 16 minus x squared over the constant. That's the adjacent side over the hypotenuse, which is cosine. So we let these two ratios, variable over constant, radical over constant, drive what the actual ratios are algebraically, and also what they correspond to trigonometrically. All right. So now I have to do something with this, and that something is substitution. All right. So.
It goes on X.
Oh, Lord only knows.
No. Oh.
No fancy math reason for that, just good old-fashioned stupidity on my part. All right, so substitution. Well, we got a lot of things to sub out. If we're using a trig substitution, what we want to do is we want to get rid of all the x's and replace them with thetas. Sometimes easier said than done. All right, what that means is that if this x has to go, it means that this whole radical really has to go, but that's easy enough. That's the whole reason why we use this approach, because I have a radical. So I can manipulate this and help me get rid of that. But also the dx has to go. All right, so most of the work is happening with actually the simpler functions. So what I'm going to do is I'm going to solve this for x and cross multiply, and x equals 4 sine theta. I'm going to do the same thing with the other one and get radical 16 minus x squared is equal to 4 cosine of theta. All right, I need a dx. So I'm going to take the derivative. Well, I have two equations that involve an x. One of them is infinitely easier to work with. So I'm going to take the derivative of the x equals 4 sine theta. That'll give me dx equals 4 cosine theta d theta. So now it's time for the fun substitutions. it gets messier before it gets cleaner, but when it does clean up, it cleans up into something that you should be able to find the antiderivative of. All right, that's the whole point. So I can swap out the x because x is the same as 4 sine theta. So let me get a new fraction bar. So 4 sine theta. I got a plus 3 that was already there, so I'm stuck with that. The radical 16 minus x squared, that was a troublemaker, but not anymore because we're going to get rid of that and replace it with a 4 cosine theta. Then, almost like as if by magic, I'm going to replace the dx with what it's equivalent to, which happens to be 4 cosine theta d theta. I mean, that's the best possible news, because those cancel out, and you have a much easier integral to work with. 4 sine theta plus 3 d theta. That we can easily find the antiderivative of, right? Okay, so the antiderivative of sine is what? Negative cosine, so this is going to become negative 4 cosine theta, then plus, well, if that were dx, I'd say 3x, 3 theta, yeah, plus c. All right, now the only thing here is, I mean, we're pretty much done. Well, we're close anyway. Because these thetas, we have successfully anti-differentiated. That was the big issue here. Now I just need to get rid of those thetas and bring it back into the world of x's. Fortunately, I have a triangle to work with. All right, and a lot of different information related to that triangle. Like, for example, the cosine of theta, you'd be like, I have no idea what the cosine of theta is. You haven't told us what theta is. Well, I didn't need to because I have a triangle there, and all I need to do is relate the adjacent side to the hypotenuse of that triangle. The 3 theta part, that'll be a little trickier, but we'll get to that in a second. So this becomes negative 4. The adjacent side is radical 16 minus x squared. The hypotenuse is a 4. So that's going to cancel also. Plus 3 theta plus c. All right, so we can clean that further in a second. So then it's a question of, all right, well, how am I going to get rid of that theta? Now, answers vary here because you could actually come up with 6 different equivalent correct answers to this problem, depending on how you look at this theta. All you need is some expression that represents theta in this triangle. Like, for example, I have an equation here that says that the sine of theta is equal to x over 4. If I wanted to get theta alone, what would I do to both sides? The arc sine. So theta would be equal to the arc sine of x over 4. All right. But you might have looked at it and said, well, I didn't use sine of theta equals x over 4. I used the cosecant of theta equals 4 over x. Or the tangent of theta equals x over the square root of 16 minus x squared. Or the cotangent is the other way around. Or the cosine. Or the secant. Any one of those ratios are fine. And they'll give you something that relates theta and x. So that's all we need. All right? So our final answer, one possible final answer would be negative the square root of 16 minus x squared plus 3 times the arc sine of x over 4 plus c. Personally, I think using the sine ratio makes sense because that's the simplest one, right? You look at all the possibilities. 4 over x over 4, x over radical 16 minus x squared, the other way around. Radical 16 minus x squared over 4, or 4 over the radical 16 minus x squared. Which one of those ratios is simplest out of the possible ones that you have? I mean, it might be a tie in your mind of 4 over x or x over 4, but they're both related to the sine function in some way. Okay? So, don't think zebra, think worse. The simplest explanation is often the correct one. I get my analogies confused. Yeah, we'll burn that bridge when we get to it. Sorry, they got my reference. How do we label a triangle? You determine based off of when you decide on A and U, whatever placement makes the third side equal to the radical that's given. So if I put, like the one that I erased, if I put the x here and the 4 there, I would have gotten a radical, but it would have been different from this radical. So any radical, any placement that allows for this radical to exist is going to be fine. To exist. Yeah, so because that's the thing that you're trying to swap out. Yeah, by Pythagorean Theorem, exactly. And you'll see in the next one it's the same idea. So we'll reinforce that. Yeah, right? Oh, you know what? This is so hilarious. I'm drawing these triangles. That's what I'm saying, yeah. I'm like taking pains to draw the triangles and I have them right there. You know, in my defense, in every other iteration of these notes previous semesters, I've never remembered to put triangles in there. This is the first time I did it and I'm not used to it. So, yeah. Okay, so looking at the 4 plus x squared, you look at that and say, well, there's no radical. So then what? Well, funny thing is, there is. All right, so even cases where there aren't radicals, you can still treat them as if they're radicals. I would normally agree with you, except you can't split the fraction up that way. It's only if the plus or minus is on the top of the fraction that you can break it up. That would be like saying, right? Let's break the mold and make new math. Yeah, it's just one of those things. Like, you could split it by sums and differences on the top and not on the bottom. All right? So I've manufactured successfully a radical. Why did I do this? Because I don't know any other way to get this antiderivative. And I just learned how to do trig substitution, so I figured why not give it a shot. All right? So here we are. Anyway, we define our U and A just like we did in the last problem, except our placement's going to be a little bit different. So, and you can kind of cut to the chase on this a little bit, because if you know that this is going to be A squared, and this is going to be U squared, then really you're saying that A is equal to 2 and U is equal to X. You know, you don't have to show that first step, which is just me reiterating what I did with the arrows. All right. So placement. I want to place these two sides on the triangle so that the third side is the radical that I want to get rid of. Okay? So I just need the third side to be the sum of the squares under a radical. Well, basically, I want the third side to be the hypotenuse. So as long as I place the u and the a as either of the two legs, I'm going to be in good shape. And you know, at least when you're practicing this stuff, don't be afraid to fail, because what will happen is, you know, like on a test, if it's the first time you're actually trying this on your own, that's going to be a problem. But it really is a matter of sometimes placing it incorrectly before you realize why you're placing it in certain, you know, certain sides of the triangle. So you might look at it and say, okay, yeah, I'll just put the x there and 2 there every time I see a problem that looks like that. Well, sometimes it requires the same concept. It just doesn't look precisely like that. You know, so what do you do then? You know, sometimes you just have to kind of play it out. So maybe you accidentally put the 2 as the hypotenuse and the x as one of the legs. If that's the case, then you know you'll get it within seconds that you're using the wrong arrangement.
But if you put the 2 as opposite or vice versa, it never will matter.
It will never matter. Yeah. I mean, the only thing is that you'll be introducing, instead of a tangent ratio, a cotangent ratio. But in the grand scheme of things, that's not overwhelming. You know, like the derivative of tangent versus the derivative of cotangent, it's not much more challenging. Okay. So I need the ratio of the variable to the constant, opposite side, adjacent side. So that's telling me tangent. So tangent of theta is equal to x over 2. Then I need the ratio of the radical to the constant, and that's hypotenuse over adjacent. So square root, I'll write it as 4 plus x squared over 2. And we want to think, and that's the only thinking step really so far, because everything else is kind of procedural. Although you could look at the triangle setup as thinking also. But yeah, I'm looking at the hypotenuse to the ratio of hypotenuse to adjacent. That's the secant ratio. Right? It's the reciprocal of what the cosine ratio would be, which is adjacent over hypotenuse. So secant of theta. All right. So what do? When we solve for x, we solve for the radical. So x equals to tangent theta. The radical, the funky radical, the reason why we're here, is equal to 2 times the secant of theta. All right. So once you make the minor adjustment to the secondary equation, that's all you really need to do with that, because this is direct substitution. I'm going to take the radical part and replace it with the trig part. But the other part, we have to do derivative. The idea behind this whole approach is to take something that was hard to do and simplify it. Right? It doesn't seem like it's simplifying it, but all this background work is to make it so that you're taking something that you can't find the antiderivative of into something that you can not only find the antiderivative of, but also easily do that. All right, so dx is equal to 2 times secant squared theta d theta. Also need to know things like the derivative of tangent is secant squared. Hopefully that's something you know, but if not, definitely put it on the list of things to know. All right, so 1 over that radical squared, well, that radical is now 2 secant theta. And the dx is now 2 secant squared theta d theta. Indeed. It's going to come out pretty nicely. Maybe an extra step to clean it up. 1 over 4 secant squared theta. cancellation here, right? 1/2 d theta. I mean, that's your payoff right there. All that work so that you get to this step and you can say, oh, all right, my antiderivative theta over 2. That's wonderful. Plus c, of course, but still. Now we just got to swap out the theta. All right, so I tend to default to whatever I came up with as my simpler equation, the u over a equation, because that's going to be easy to work with. Again, you could choose any ratio out of the triangle and work off of that. But I know, because it's written right there, because I had to write it at some point, the tangent of theta is equal to x over 2. So that would mean, or imply, that theta would be equal to the inverse tangent, or the arc tangent, of x over 2. So now I have a definition of my theta as arctan x over 2, all over 2, but I'm just going to chuck a 1/2 in front to account for this guy, plus c. And actually, this is a modification of the proof of the shortcut rule for arctangent. If I had actually left all this stuff in terms of u's and a's, I could have actually come up with a general rule for the arctan of u. And I'll just give it to you at this point. But if you look at what we started with, it really had the form of 1 over a squared plus u squared. Right? I mean, I have a 4, but that was some a squared, right? Dx. So what did I end up with? 1 over whatever the a is times the arctan of x over whatever the a is plus c. And actually, I should be more clear about this. It only worked, it's not really the general rule. It only worked because it was, the u was equal to x. But, so it's really 1 over a squared plus x squared. But it allows you to deal with cases where the, where it looks an awful lot like the arctan derivative, just you're off by a constant not a constant, but just a constant instead of a 1. So, if you think back to when we were finding derivatives of arctan, involving arctangent, we very often end up with stuff that looks like this, and it's just looking back. But that would be a rule, but, how many rules do you want to remember? The trig substitution approach allows you to come up with these regardless of rules, right? Because if you know this rule, what's to stop you from saying, okay, well, now I got to find a rule for arc sine, for arc cosine, arc cosecant. Like it's not user friendly that way, in my opinion. All right. Ooh, look at that. It's good stuff. Substitute.